Hello students. Today we're going to be looking at applications involving exponential functions. With this we'll be discussing exponential growth functions. So let's just look at these exponential growth functions. As they change with time, you can see they all have the same general shape. If I look at just any sort of e raised to some power k as a function of time, and we'll discuss the doubling time a little bit later, but let's go ahead and look at an example because we've looked at exponential applications before. I graphed the two functions that they want us to discuss. One has to do with the population of the town pine and the other the population of the town spruce. Each one of them has an initial population of 1500 at time 0, and that's about all they have in common there, because as time moves on, spruce is increasing at an exponential rate, whereas pine is increasing at a constant growth rate. So let's just look at that plain growth rate. Now growth rate is just p prime of t, and that would be 125. So every year the population increases by 125 people, whereas s prime of t is equal to, I'm going to take this derivative, which is just a constant times an exponential. So take the derivative of the outside, leave the inside alone, and then multiplied by the derivative of the inside. So that's going to be e to the 0.1 t times the 0.01. You'll notice that this is s of t. So the growth rate of this town spruce is 0.01 times s of t. And what this means is that its growth is proportional to the population. So every year this population is going to increase based on what it was that year. Relative growth rate is another aspect we can look at, and what you'll do for relative growth rate is you will just take the derivative or the growth rate, and you're comparing it with that population, or you're taking that ratio, so it is just the p prime of t over the p of t. And with this you're going to get 125 over 1500 plus 125. And as we increase in time, we see that the relative growth of this town pine actually decreases with time. So next up we'll look at the spruce, and we'll do the same kind of procedure. We're going to compare it with itself, and so I would get 1500 e to the 0.1 t times 0.01 over 1500 e to the 0.1 t. These guys cancel, leaving me with a relative growth rate that is a constant. And this constant relative growth rate is the main difference here between this linear growth rate and this exponential growth rate when I'm talking about relative growth rate. In this next example, we're to come up with our equation for the particular scenario that they've presented us with here. They tell us that we're assuming a world population of 6 billion at time 0. That they just gave me why not, so we're going to say everything is in terms of billions, our y, so this is going to be a 6. E to the k is something we are going to be looking for, and they tell us at time 10 the y value here, or the population total, was 6.9. So what I'm going to do is solve for k, and I'll move the 6 over, take the natural log of both sides, and divide by 10. After doing that bit of algebra, I get 0.014 for k. That gives me as my exponential growth function y of t equals 6 e to the 0.014 k as my function. B says find the doubling time. So finding the, oops, I wrote a k, I meant to write a t. Sorry about that. B says they want me to find the doubling time for this. Now I can use their doubling formula, if you will, or I could just figure out how long it would take for the population to double. I would just let this y of t value equal to 12, and I could just solve it from there, or I can use their little formula. Either way, it really doesn't matter, you'll still get the same thing. So if you will, notice that what I end up with is the natural log of 2 over that k value, which is what they told me the formula was, but I don't really need that formula. Alright, I'm to find the absolute growth rate, which means that I'm going to find the derivative and graph it for C. Okay, I found that derivative, and I found that the growth rate was increasing exponentially. This was how I adjusted my window. And then how fast was the population growing in 2010? So what they're asking me to do is, and they told me that t was 11 there, they're asking me to just plug that into my growth rate formula, which is the y prime. So I'll do that and get that value. Alright, I did that, crunched the numbers, and I got roughly 98 million people per year is how this growth is changing. It is increasing at that particular rate. Alright, a little financial problem. $500 is our initial investment, so I can put a 500 here. E to the k. After 1 year, I earned 6.18% interest. So at time equal 1, I made 500 times this interest. So we will just write 1.0618, so we don't have to do any addition. And then I'll get that k value. Okay, I got that k value. That means my growth function looks like, there's my 500, e to the 0.06 t. They want to know, next up, they want to know how long will it take the balance to reach 2500. So for the next part, 2500 equals 500 e to the 0.06 t, and what I'm going to do there is just divide by the 500, take the natural log of both sides, and I'll get that time. Alright, so I did that algebra and ended up with about 26.8 years. Similarly, they tell us that power follows this growth rate function, and I'm to find the power function beginning at 2006. My initial power would be 7,000 e to the k, and then they tell me after 1 year it had an annual growth rate of the 0.02, so I'll say 1.02 so I can get that total value, and then I'm going to get my growth rate using algebra. I'm going to divide and then take the natural log. Alright, I got that k value to be this 0.0198. That would mean my power function, just putting all of that together, is the 7,000 e to the 0.0198 t, and that would be the answer to A. Question B wants me to find the total amount of energy used, and they give us this equation here to tell us the total amount of energy used. So I'm going to say total energy used is going to be this integral of my power function. Now my limits of integration, they want to know during the year 2010. Well, if 2006 is 0, 7 is 1, 2008 is 2, 2009 is 3, and 10 would be 4. So during the whole year, that would be from 4 to 5, and I'm going to integrate my power function, which is 7,000 e to the 0.0198 t dt, and I'm going to integrate that and plug in my values, and I'll crunch those numbers for you. Alright, there's what I get for B. They don't tell me to put in any particular units, probably not standard units, but I'm going to leave it. And C, they want me to give the total amount of energy, so total energy used between 2006, which would be 0 to any time t, of our function. Now we're going to say that the energy used when we first start up at 2006 is 0, so you might say that E of 0 is 0, and we'll just assume that to be true, and then I would just write down what I got last time. Oops, 198. I'll fix that and write it all. Alright, just substituting in. This is just an algebraic equation. Then I could say this is the total amount of energy used at any time t after year 2006. Alright, we're going to do some radioactive decay problems. I need to figure out, let me just go ahead and write down that y of t equals y naught, because I know it is a decay problem. This k is negative, and I need to come up with this k value. They go ahead and, I don't really need this equation, but I'll go ahead and use it. I could do it as I have worked the other problems, but the half-life is, I probably should do it over to this side. Okay, so the half-life in years is 5730, natural log of 2, and solving for k, I get that k is about 0.000121. So that's my growth rate, and it is not really a growth, it's actually a decay. And we want to know how this bone is, and this bone is, there's about 30% of it left. So however much it is that you find, you know that y of t, or your y value divided by your original, is about 30% left. So that's going to be 0.3 e to the, so you could say that if you started off with, let's say, 100 here, then that means what you would have left would be 30% of that. So then you would only have 30. So if you start off with 100 grams, you'd only have 30. So when I did that division, I'd get 0.3. You can put in whatever numbers you like. Now I'm going to take the natural log of both sides and find that t value. Alright, when I crunch that in my calculator, I get 9,950 years. Old bone. On to the last one. One more problem related to decay. I'm being told that the amount of a drug in the blood decays at an exponential rate. My y naught is 100. That's handy. And let's write y of t equals. And the half-life of the drug is 16 hours, so 16 equals natural log of 2 over k. That will give me as my k value approximately 0.0433. So this would be my growth rate formula. So there's my function. There's the answer to A. How much time is required for it to reach 1% of the initial dose? So for B, I'm going to have 1% left. That means that what I'll have left is a 1 over here. So for B, I'll have 1 e to the minus 0.0433 t. I'm going to go ahead and divide by 100, and of course over here I get the 0.01, which I could have just started off there, but anyway, I went ahead and put that other in. Then I'm going to take the natural log of both sides and find my t. Okay, I get 106 hours for that. The C question is a little wiggly. Let's see. I give a dose 12 hours after the first dose. How much time is required for the drug level to reach 1 milligram? Okay. Let's see how much drug is left in his system after the 12 hours. So I want to know what y of 12 is so I can figure out how much is left. And that's just going to be the 100 e to the minus 0.0433 times my 12. If I number crunch that, I am going to end up with the 59.5 milligrams is going to be left in the system. Okay, so right now I get an injection, or he does, of 100 milligrams. So now in the blood, my new y naught is going to be 159.5 milligrams because I now have been given a shot. In addition to that, I still have the same decay rate, and I need to know how much time until I only have 1 milligram. And what I'll do here is I will divide by the 159.5, take the natural log of both sides, and solve for t. Okay, when I complete that computation and that little bit of algebra there, I get 117.1 hours. Cool. That concludes section 9 of chapter 6. See you at the Collaborate.